Steven. You're welcome to AFD'S Academy. Today, we're going to be dealing with carbohydrate and the essential aspect of carbohydrates, where we're going to talk about monosaccharide and other jobs which we're going to do. But let's begin from the beginning. Carbohydrate is a compound consisting of carbon, hydrogen, and oxygen. But most essentially, carbohydrate is a polymer. Polymer means that it contains a whole lot of monosaccharide that fused up together to give us this carbohydrate. So we're going to go straight to the essentials, which is the classification of this carbohydrate. We have the monosaccharide, we have the disaccharide, we have the oligosaccharide, and we have the polysaccharide. So let's take the monosaccharide and see what we can make out of it. We have some important jobs to do in the monosaccharide, some basic things we must understand in order for us to be able to fuse our rings together in the disaccharide section. So if we miss the essentials in monosaccharide, we'll find it difficult to comprehend our disaccharide. So it is important that we focus, we pay attention in this first area which I'm about to begin with, so that it will be easier for us to move along with other aspects. Now, in monosaccharide, these are simple sugars that cannot be hydrolyzed further. We can't break them further to get any other thing. We have a couple of examples and their structural formulas. So it's not just knowing them by name, like glucose. You should also know the structural formula of glucose, the structural formula of mannose, of allose, artrose, galactose, fructose, and so on. There are many of them. So I will state their structural formula, then I'll use them to explain what we are supposed to do. Now, in this monosaccharide, we have the aldose sugars and the keto sugars. Aldose sugars means their functional group are made of aldehyde, and the keto sugars means their functional group are made of what? Keto functional group, which is the ketones. And we have various classes. We have the 3 bonded, we have the 4, which are the tetroses, the trioses for 3, tetroses, pentoses, hexoses, and so on. The simplest being our glyceraldehyde. And so I'm going to make use of it and others to explain the dextro and laborotatory. So first of all, let's take the example of monosaccharide. So these are simple examples. I have a whole lot of them, but because of the space, let's take these ones, use them to elucidate. Now, the first one here is glucose. The second one is the mannose. The third one is the galactose. The next one here is the fructose. And this is the allulose. So if you look very well, you see that these are aldol sugars because they have the aldehydic functional group. But this is a keto sugar, fructose, because it has a keto functional group. Now, all these, because due to isomerism, all of them exhibit a enantiomerism. Enantiomerism means that they have the ability to rotate a plane polarized light when light passes through them. Now, most of them rotate the light to the left, while some rotate to the right. Those that rotate to the right are called dextro-rotatory, while those that rotate to the left are called levo-rotatory. So we have the D sugars and the L sugars. So how do we know the dextro-rotatories and those that rotate to the left? Now, the last OH group before this CH2OH, the last OH group, if it is at the right, it is dextro. If it is at the left, it is levo. The same thing goes here. So all of it, this is D-glucose, D-mannose, D-galactose, D-fructose, and D-allulose. So I will take the structures, I'll clean them out. But like I said, it is imperative that the first thing first, before you do anything in this course, which we want to deal with today, first you must have these things offhand. There is no way you're going to draw the pyranose group structure of this, which is the ring structure of this. You can't draw it if you do not know the structural formula. So this is the number one thing you should learn first. Now, let me break it down in terms of maybe probably using one to give us examples. So we're going to make use of glucose. Now, this is our glucose. So this is called D-glucose. Now, if I have this, this is L-glucose. Why? Let's look at this. Now, this second to the last OH is at the right. That is why it is called D-glucose. But in this other case, it's the same glucose, but the last OH is at the left. So it is called L-glucose. So this is as important as it is. So we are going to proceed from the ring structures we have here. We are going to learn how to form our ring structures so that we can use the ring structures to bond in the disaccharide section. So let us see how that can be done. I will use glucose and many others, but let me begin with glucose to see how we can have that done. Now, in the ring structures, we have the pyranose and the furanose. Now, the pyranose structure means it has a structure of pyran, okay, and the furanose structure means it has the structure of furan. So, the pyranose structure, this is how we're expecting it to be. While the furanose, this is how the structure of furan is. So now our next job is how can we use this structure to form a pyranose or a furanose, as the case may be. So I want us to get our pyranose structure. But furanose, many a time we always use fructose because of its keto group. We use it to form our furanose. But for the time being, let us get our pyranoses from these aldohexoses. So let me start. I will save us the long story and give you a very short way in which you are going to go about that. It used to be very technical, but if you miss it, you miss it. So this structure now This is how it's supposed to be. This aldehyde group have a double bond here and probably hydrogen here. So 1, 2, 3, 4. I have my OH, 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 OH. So this, you must understand that this carbon is what? 4 bonded. All carbon atoms are tetravalent, which means this is 1, 2, 3, 4. Now, for us to form our pyranol structure, we use that last OH and form our ring structure with it. So this is going to go. Let me move it here. I will have this, the next one here. This is OH. Now I have my hydrogen here, and here is my OH. If this bond, this is the OH, this OH here, will move in this form, drop the oxygen, and come over here with the hydrogen. The hydrogen will move. There will be a movement here to here, which gives us O negative. With that hydrogen that comes, will give us a hydrogen group. So this is what we are now going to get. Now, when you have gotten this, the next thing is, if this structure were to be pulled towards this direction, this is what you are expecting to get. We now have something like this. From here, I want to also say something else. We have what we call alpha, maybe alpha glucose and beta glucose. All right, alpha glucose is if this OH so formed is at the right side of the compound, it is called alpha. If this OH is at the left side, it is called beta. So remember, this is D-glucose first. So this, if this is alpha, it becomes alpha D before I continue. Don't forget that, it is important. So now this is what I have. From here, I want to form a ring structure. And now you should take note that all the OH and hydrogen at the right side will always be at the down side of this structure. Now, all those at the left will be at the upside of the structure. This, I can also make it to be in this form, like this one is, I do the same, but let me save the time and just proceed. In the next structure, I'll do that. So that one is first at the right, so my OH is down. The second one, OH is also down. The third one, hydrogen is down, which means OH is up. This one, hydrogen is here, hydrogen is here. Carbon 1, 2, 3, 4, and this is 5. So I've taken my 1, 2, 3. The fourth one, OH is down. Hydrogen is up. And the fifth one, which is this, you have hydrogen and CH2OH. So I have CH2OH and hydrogen. Now, what is the name? Remember, I said OH, the OH is at the right, so it's alpha. This last OH down here is at the right, so it's called D. So I'll say this is alpha D glucopyranols. So alpha D glucopyranols. This is the pyranol structure of glucose. So our job majorly will be to form this. It is as important as that. If we cannot form this, then we've not started. So we should all learn how to form this structure. We're going to do a whole lot of them. So let's try another one and see. This is for glucose. Let us do for, let's say, mannose or galactose. So I'm going to clean so that I can have another structure down. right, now I have my CH2OH, 1, 2, 3, 4. So I have OH here, OH, OH, and OH. This is D-galactose. Now, the next chemistry is this. CH2, okay, let me leave it at this. I have my 1, 2, 3, let's put it here 4. Remember, if I'm looking for alpha, means when I move my bonding process, the OH will be at the right. So I will save that energy of doing all of that. I just put my OH here, it's at the right, that's alpha. My hydrogen is here. From here, I want to take it from this way. Call it O here, this way. So that one is settled. That's from carbon 5. Remember, this is 1, 2, 3, 4, 5, 6. These are hexoses, means there are 6 carbon. So this is 1, 2, 3, 4, 5, 6. Now, but because I want to, this particular one, okay, let me just continue first. Let me not save us the stress. This OH is here, and this is my hydrogen. This hydrogen is here, and this is this. And this one is here, my hydrogen is here, and this one is here. Remember, it is 5 that will go. So I want to break this for a reason. I take this out. So this is the 5 that will go. This OH in the 5 will go here. Now what is left is hydrogen and CH2OH. So I'll put my CH2OH and hydrogen. So this is complete. So I have 1, 2, 3, 4, 5, 6 carbon. That is complete. I'm trying to, if you know how to get this, then the job is half done. So now I will form my parallel structure. Now my OH in galactose, the alpha is at the right. Then the right side again I have another OH. Here the right I have hydrogen down, so OH is up. Here again I have hydrogen down, OH is up. Here I have hydrogen down, and the H2OH is up. Now put all my hydrogens. Now this is alpha D galactose. The other one was alpha D glucopyranose. So this is galactopyranose. Since we have formed the structure, normally it would have been alpha D galacto or galactose. But this is the pyranose structure before it becomes alpha D galactopyranose. When we are bonding them in the disaccharide, the whole chemistry changes. But let us understand how we are doing this first of all. Then we'll succeed further. Now, I want to deal with beta D glucopyranose. So, in that sense, this is what I'll do. This is my glucose. Now, glucose is this. Now, if I want to have a beta structure, this will be this. 1, 2, 3, and this is my 4. So the first one, my OH will be here because I'm dealing with beta, and this will be hydrogen. And this one, OH is here, and hydrogen is here. This one, hydrogen is here, OH is here. The next one, OH is here, hydrogen is here. This one has gone. Remember, this compound is the one that will go to form the ring. Then I'll take this one, either here or here, and bring hydrogen here. So in that sense, this is my CH2OH, and this is hydrogen. Then this one that will go will come this way. This is how it is now. I'm trying to move gradually so we understand. Now, you may want to ask me, why am I not writing, like here it is CH2OH. Now, if I'm writing it this other way, remember, this bond is bonded to carbon. So the C will still come first. CH2OH. It cannot be bonded to, maybe I'll write it H2C, or, okay, let me put it this way. I'll still write CH2OH, bond it to this carbon. No, I will not do that. If you do that, it's wrong. This carbon is supposed to be bonded to a carbon atom, not to the hydrogen atom. So that's why I have to turn it this way. I guess you understand that. So now, if that is the case, let's see what we get. Now I want to form my parallel structure. The first hydrogen is down, OH is up. The second one, OH is down, hydrogen is up. The third one, hydrogen is down, OH is up. The fourth one, OH is down, hydrogen is up. And the last one, hydrogen is down, and CH2OH is up. All right, this is beta D glucopyranose. So this is a beta structure where the B is this way. If it is the OH is this way, if the OH is down, it's alpha. And these are all D. If I put the OH this way, it is L. B, which is beta. If it is this way, it is alpha. Do not forget that. We are going to use it very soon. Let's form another ring structure of, have I done mannose? Okay, I don't know if I've done mannose, but let's do it again in case, if we've not. Or let's deal with allose. Allose. I have this. OH, 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 OH. All the hydroxy group are at the right in allose. So this is D-allose. Now I can form my parallel structure without doing all of that. I hope you know that. So I can just move forward. All I'm trying to do is to get you acquainted with this. So what did I want? If I want alpha, means the OH that will form here will be down. The next one, OH is down. The next one, OH is down. The next one, OH is down. This one is the one that goes to form the oxygen bond, but then I have my CH2OH. So this is alpha D allopyranose. So this is allose. So it's allopyranose. Now I'm trying to, the more I solve them, so you become acquainted. We just forming the ring and we proceed. Well, once we have mastered the process of forming our ring, then we are halfway done. Then we can move on. Now let me do example of fructose, which is a keto sugar. Its own system is different. So its own structure too will be different. So let me take this out. So I have CH2OH, CH2OH. Now, if you look here, you realize that here we have a keto sugar in between with a CH2OH instead of CHO, which is an aldehyde group. But now this is our functional group, which is a keto. So our bond process will move down to here. So that's how different it's going to look. So this is first of all D-fructose. D-fructose. Now, just permit me and let me do some chemistry. Remember, I'm supposed to get my OH group somewhere here. When I move this oxygen here, oxygen will be left, the hydrogen will form the OH, will join with this to give me the O. Now, this other guy will either be at the left or at the right. So if this is at the right, it's alpha. If the OH is at the right, it's alpha. If it is at the left, it is beta. So I will be having something like this. Remember, this is 1, 2, 3, 4, 5, and 6. Now, this is what I'm going to have. This particular carbon here is this carbon 2. And I have this. Remember, I said the OH, if it is at the right, is alpha. So what is at the left? This is now at the left. Alright, so I have my CH2OH is at the left. Remember, this is carbon 1 and this is carbon 2. Now, I know the bond formation is this way. Let's leave it. I'll join it. So we're taking care of carbon 1 and 2. Now, carbon 3, the hydrogen is at the right, the OH is at the left. In carbon 4, the OH is at the right, the hydrogen is at the left. In carbon 5, this is in carbon 5 here. This oxygen is what has been taken over. So let me say I have shifted this one, I shifted this one a little bit to this side or this side and move the hydrogen this side. So in this carbon, I have the CH2 here, OH, this one, I turn it to this direction. I move my hydrogen to this direction. Now the oxygen bonded line now comes through this direction, which is this. So this is how it goes now. So I have carbon 1, 2, 3, 4, 5, and 6. Now this is a furanous structure, it's not pyranous. So I will be having something like this. Now, since I left the OH at the right, so my OH is alpha. So this is my OH here at the right. Now, this other side, I have CH2OH. So this is 1, and this is carbon 2. Carbon 2. So carbon 3, I have hydrogen down, and I have OH up. Carbon 4, I have OH down, and hydrogen up. Carbon 5, I have hydrogen down. I have my CH2OH. So this is 2, this is 3, this is 4, this is 5, and this is 6. So this is a furanous structure. So this becomes alpha D fructofuranous. So this is an alpha D fructofuranous. We're going to bond them later, all right? But for the time, let us understand how we get all of it. Then we can do the bonding later. So we've done a couple of examples. I don't know if I should do more. Okay, let me do two more. I've dealt with allos, so let's handle arthros. Then arthros, we just move on to maybe mannose. Yes. Then we move to our disaccharide so that we can see what will happen. So let me take this. So arthros, I have my CHO. I have my CH2OH. 1, 2, 3, 4. So arthros, I have my OH here, the rest are here. So this is D-arthros. Remember, when we have all of them here is allos. Alright? This one is this way is arthros. So I do not want to do the second and all of that. I just want to form my ring structure now. So this is it. Alright. If I keep my OH at the right, it will be down here. And here will be hydrogen. This one is at the right is down, OH is up. This one at the right is down, OH and hydrogen is here. This one is at the right is down, OH is here and hydrogen is up. And this one will go. So this will give me my CH2OH and this is hydrogen. So this is alpha D arthro pyranose. So that is how we're going to roll now. I'm not going to be, by now you should be conversant with the process of forming this, all right? So that we can just be quick. Now, the last one before I bond the two of them together. The last one. So I have my this. 1, 2, 3, 4. Galactose will be this. If it is mannose, mannose will be OH, then the rest OH. Go and learn the structures. This is D-galactose. Now I move straight to here. Here I am. If I want it to be at the left, let's say we'll keep it at the left, so it's beta, alright? So left OH should be here, and this other right side will be hydrogen. The next carbon OH is down, and this side is hydrogen. The next one hydrogen is down, and here is this. The next one hydrogen is also down, and this is up. This one is what goes this way, and I'm left with this, which is CH2OH, and here is hydrogen. So this is beta. So this is beta D galactopyranose. Now, this is all about the monosaccharides and their ring structures. So we have been able to understand when is a sugar said to be D sugar. That is when the OH down here is at the right. The OH before the last carbon is at the right. It's called D sugars. When the OH down before the CH2OH is at the left is L sugar. When do we say it is alpha? When the first OH, when we want to form our pyranose structure, is at the right, we call it alpha. If it's at the left, we call it beta. Now, one thing is certain, that they are all enantiomeric, which means they all rotate plane or polarized like to either left or right. What is enantiometer or enantiomerism? Is when this carbon, for example, I will call it a chiral carbon, when the compounds or substituents attached to this carbon, all of them are different. Here is OH. If this carbon here is a chiral carbon, which makes the compound enantiomeric. This is chiral because this is different from this, and is also different from this, and it's also different from the rest. So all the four components attached to this carbon are different: OH, hydro group, hydrogen, and all of it. So this compound is enantiomeric because it has a chiral carbon, and having a chiral carbon means it can rotate plane or polarized light to either left or right. So that is why we're having D-glucose, L-glucose, D-mannose, L-mannose, fructose, and so on and so forth. Now, disaccharide. Disaccharide is going to be quick because we now understand how this is done. Let's see how that goes. Now I'm going to bring glucose, one, two, three, four. OH, 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 OH. You practice. If you do not practice, you will not know which one will be where. So this is D-glucose. Let's take another one. Galactose. CH2OH. 1, 2, 3, 4. I have OH, 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 hydrogen. So this is the galactose. Now, disaccharide is the condensation reaction between two monosaccharides. The two of them condense. In the condensation reaction, there is an elimination of a water molecule in the process. So, for us to do that, we must, first of all, form the ring structure of this and the ring structure of this before we bond them together. Now, let me form the ring structure of this. The ring structure of glucose is this. One, two, please. Let me redraw this. This is, and the next one is that of galactose, which is also almost in the same form. Now, I want to give us a D-glucose. No, alpha D-glucose. Let's call it, this will be alpha D, and this will be beta D-galactose. Now, alpha means OH is down, hydrogen is up. The next one, OH is down, hydrogen is up. The next one, hydrogen is down, OH is up. The next one, OH is down, hydrogen is up. This is what forms the other, and I have my CH2OH and hydrogen here. This is my alpha D glucopyranose. Now, the other side, I want to form beta D galactopyranose. I will now have beta OH is up, hydrogen is down. The next one, OH is down, hydrogen is up. The third one, hydrogen is down. Hydrogen is down. Which one is that? 1, 2, 3. 1, 2, 3. Okay, good. Hydrogen is down, OH is up. The fourth one, hydrogen is down. Yeah. OH is up. The fifth, this will go. Then I have CH2OH and hydrogen. Now, this is alpha D galactopyranose. Now let's join them together. Now we say that condensation reaction is a reaction between two monosaccharides which has to do with the elimination of water molecules. So where we then react, this OH will react with this OH, all right, to remove water. Now I have H2 and 2 oxygen. So if I take out this OH, I take out this OH and I bond them together. This is oxygen bonded. What is left is water, and this is my water that will be left. Okay, so this is the water that will be left. Then this is what I have. So in this case, how did I bond it? I bonded carbon 1 and carbon 4. So because of space, I will write it upward here. I bonded carbon 1 and carbon 1, 2, 3, 4. So this is the name. I have alpha D glucopyranose because I'm proceeding. In brackets, carbon 1, 4. The bonded are carbon 1 and carbon 4. 1, 4. This is beta. I'll continue this way. Beta D. Was it galactose? Yes. Galactopyranoside. Now remember, our first step was to have our pyranose structure and another pyranose structure of galactose and that of glucose. We have mastered the cause of giving these ring structures. That is number 1. Number 2, we condense them in disaccharide because in disaccharide we have to bond 2 monosaccharides. Now the positions in which the bond is very important to us, which is position 1 and position 4. So from the first one, which was alpha D glucopyranose and beta D galactopyranose, when we merge the two of them at position 1, 4, it becomes alpha D glucopyranosio, because I'm continuing, 1, 4 beta D galactopyranoside. So this is the structure of that. Remember, we say monosaccharide is the condensation of at least 2 molecules. Oligosaccharide is 3 and above, which means we are still going to, if we want to get to oligosaccharide, we do this and we bond with another. So I will try to reduce the size of these things when we get to that level. But then let's try another one again, another disaccharide. Okay, in another disaccharide, let's say, yes, let's take galactose and fructose. This is my galactose. This is alpha, no, this is D galactose. And here is fructose. I have my this is D fructose. Now, they are ring structures. The ring structure here will become and this one will be it to be, this one, I want it to be alpha, which means OH will be down. The second OH is down. The third hydrogen is down, OH is up. Okay, the fourth hydrogen is down, OH is up. And this last one here will form the ring, and this will give me my CH2OH, and this is my hydrogen. So I put my hydrogen all through. So this become D alpha D galactopyranose. Now I come back here. Remember, I want the OH to be at the right. In this case, so it will be down. Here will be CH2OH. So I've taken care of carbon 1 and carbon 2. So I have 1 and 2. The third one, hydrogen is down, OH is up. The fourth one, OH is down, hydrogen is up. The fifth one here, I have my CH2OH and hydrogen is down. So this is alpha, because OH is down, alpha D fructofuranose. This one is alpha D galactopyranose. Now, during condensation, the hydrogen group, the oxygen, OH group, will have to bond together. So in this case, this OH will come down to bond with it. So I'm going to take it out. OH is out, OH is out. So this will go with this. And we have water. Remember, I have OH here. I also have OH here. If I take one of the oxygen here to put in the middle, which is this, what is left is H2O, which is this. In condensation reaction, we remove a molecule of water in the process. So now, the bonding procedure is this. This one bonded from 1, and this one is 6. The furanose structure is 6, carbon 6. 1, 2, 3, 4, 5, and 6. While here is 1, 2, 3, 4, 5, and 6. Now, what is the name? We come back. Remember, it was a galactose. So this is alpha D galactopyranosio 1, 6, bonded from carbon 1 and 6. Alpha D fructofuranose. So that is it. Alpha D galactopyranose 1, 6, alpha D fructofuranose. So this is it. This is a disaccharide. So we've not started oligosaccharide, but we're going to do at least one of oligosaccharide before we can move out. So should we do another one? What if we bond 2 molecules of glucose? All right, which would be maltose, the disaccharide name. So if we bond 2 molecules of glucose, how is the structure going to be? So let's try that one. So I'm going to take this out. So this is my glucose. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Glucose, OH, yeah, and OH. Now, this is D-glucose because the OH before the last carbon is at the right. This is also D-glucose. Now, let's say call them both alpha, then I would be having something like this. Remember, this is our pyramidal structure. First of all, it's going to take its normal form. And this side again. Okay, this is my two parallel structures. Now, if they are both alpha, so the OH this side will be at the downside, which is right, hydrogen will be up. Then the next one is also down, hydrogen is up. The third one, hydrogen is down, OH is up. The fourth one, OH is down, hydrogen is up. And the fifth, give me my CH2OH and hydrogen. So the same thing play here. So I just have to copy this one here. Hydrogen, OH, OH, hydrogen, OH, hydrogen, OH, hydrogen, and CH2OH and hydrogen. Now, these two want to bond. This is alpha D glucopyranose, alpha D glucopyranose. So if I bond the two of them together, remember I will remove a molecule of water, which is this. So I will take this OH and this OH will go. So they will be bonded to oxygen here, and this is the water molecule in the condensation. So the name becomes alpha D glucopyranose 1 carbon 1, 2, 3, 4. So 1 and 4 bonded. So it becomes 1, 4 alpha D glucopyranoside. So by virtue of this, we can do as many as possible. When we, first of all, know their structural formulas, we know their ring structures, then we can form any compound we want. Be it a furanose, a pyranose, whatever we want to condense, we can condense. So I'm going to do one more, just one last one. I am not going to take this out, so let me just add to it. Maybe mannose, perhaps. So we have this. So here is our mannose. So let me form its own ring structure. This will be oligosaccharide because I'm about to condense 3. So in mannose, this will be, let me take it alpha, or anyone, probably alpha. Here, hydrogen is up. Here, hydrogen is down. OH is up. Hydrogen is down. OH is up. OH is down. Hydrogen is up. And CH2OH. So if I have to condense with this, I can now take this out again. You see that? So let me roll the plus now. So the name continue. Pyranose. Here is 1, 4, 2. Okay, this is alpha D glucopyranose 1, 4. 1, 4 again in bracket. 1, 4. Was it alpha? Yeah. Alpha D mono pyranoside. So this is an oligosaccharide because I have to condense 3 structures more. So I can bring a fructose somewhere here. Fructose always has the CH2O up. If I do that, I will have alpha D glucopyranosyl 1,4 alpha D glucopyranosyl 1,6 alpha D fructofuranoside if I have to merge it with fructose. That is in oligosaccharide. So it is important, if we understand the basic principles, which is number one, how to know their structure. If I say glucose, you know the structure, mannose, galactose, fructose, allose, atrose. If you know that first, these structures first, then you are halfway up. Second, how can you use these structures to form their range structures? I have illustrated about 3 or 4 examples how that is done, and now you can see we can do it without following that principle, which means in terms of exams, you don't need to be doing all of that. If you remember this, you can remember this. Directly, you move. And now, thirdly, in disaccharide, we say we're going to condense them. So I condense this monosaccharide with this monosaccharide, I get a disaccharide in 2. And that is alpha D glucopyranosyl 1,4 alpha D glucopyranoside in 2. Now, we say in oligosaccharide, we can condense 3 or more. So I can make it 4 if I want to. So I can now still condense, add another one, and the language continue. Then in polysaccharide, summarily, I don't think there's not much there. In polysaccharide has to do with at least 10 of these rings and above. So in the case of polysaccharide, let's call cellulose. Cellulose has to do with the condensation of what? Glucose molecules from about 250,000 to 10,000 units of this. So imagine 250,000 to 1 million, sorry about that. 250,000 units to 1 million units of glucose condensed molecules give us cellulose. So which means if these were to be glucose too, these all of them, let's say they are all glucose, all I will need to do, I'll do this and put N. Which means this condensed with this and this N tell you the number. I can put here 500. So that becomes my cellulose, means I have been able to condense this and many thousands of them. 500,000 perhaps is my N, where N is 500,000. That is for my cellulose, and I'll write it down here, cellulose. The same thing happened to others, glycogen and all of that. It is still the same condensation of thousands of this monosaccharide. So like I said, carbohydrate is a polymer consisting of many monosaccharide or monomers of simple sugars bonded together to form that. So the carbohydrate you see is not just one guy, you have thousands of ways. The same thing goes to starch and many other ones. So we're going to shut down today. Probably we're going to have the other aspect where we are going to bond the simple sugars with amino acids, and we see how that happens. And the glycosides, we'll go a little further again, and even the condensation of what amino acid too on its own case. Too, like we're doing this, we do the same. Amino acid bond together to give us protein. Okay, this one bonds to give us carbohydrate, so and so on. That is how it is. So basically, or most importantly, do not forget to first know the structure of your glucose, your mannose, your galactose, your all of that, and how to get their range structure. If you do that, I guess you're going to be fine. Don't forget to subscribe and press the like button, and also on your notification bell, so whenever I make an update, you're going to get it. And by so doing, we're going to go further. Thank you, and have a nice day.